Okay, it's 8:01, so let's go ahead and get started. Okay, I'll be doing an announcement um, as well over Canvas, but for the final exam, I am going to want um, to see your work on the final, and so and I may even want to see a little bit of work on the next exam chapter 16. So you will need to uh, find a way um, to create a PDF. I will only be accepting PDF files, and work needs to be done in sequential order. Um, so you can scan it and turn it into a PDF. There are apps to take a picture and turn that into a PDF, but I'll only be accepting PDF files. Uh, it's just too much of a nightmare to try to put all of your JPEGs in order and try to sort through them at this point. And I think also there are a lot of other, um, as this distance learning thing goes on, um, this is pretty much going to be the standard for turning in written assignments from here on out anyway. Um, so the final exam will not be a exam format. It will be a take-home format in which you will be given 24 hours to work on certain problems, and those problems will then need to be submitted through PDF. Yeah, absolutely. The question was, can you write on OneNote and turn it in as a PDF? Yeah, as long as the format can be done, um, whether you want to type it up in Word and turn that into a PDF, if you have Adobe and you can create a PDF, if you want to, take a picture and then import the image into a um, Word document and then turn that into a PDF, however you want to do it is fine. I just want the file to be one standardized format, if that makes sense. As long as it's a PDF version. Okay. So it doesn't have to be, um, it doesn't have to be uh, paper and pencil necessarily, as long as I can see that it's your own work and not somebody else's work. I need it to not be plagiarized. And so again, the final exam is not an exam format. The final exam is take home. There will be a number of problems that I will upload, and then you'll have a 24-hour turnaround on that. Okay, makes sense. Okay, so again, secure a way to create a PDF from your own work. Okay, now many people already have that ability. They have scanners, they have printers, they have, things that they can do. Some people don't. So there are apps out there, free apps, I think, where you can take a picture and turn it into a PDF, sequentially. Again, I don't want, 17 different PDFs. If I want one. I want one file that's from you for your work. Okay, in sequential order, not, problem number 7 before problem number 3, and then problem number 5. It's just becomes a nightmare trying to grade all of that, as you could probably imagine. Okay. Now I'm still debating on whether or not I want to do this for the next exam. I think that for the next exam, it's gonna still be the same format as before. But just be prepared that if I do require you to submit your work on a problem, I may select a problem or two that you are able to now only select a problem or two. It's not going to be as big of an issue because it's just not. If you can still submit a picture or a JPEG on a problem or two. You know, if I ask you to verify your work on the next exam, you know, on a certain problem, then you'll be required to submit that to me. Okay, whether it's a problem or two. I may not ask for all of them. I think that would be overkill at this point. But yeah, just, you know, I just want to make sure that there's some sort of verification that you are doing your own work. Okay. Okay. But again, yeah, the next exam is in WebAssign. It will be in WebAssign. Same format as before. I may do 2 submissions instead of 3 this time. I think maybe 3 was overkill last time. But yeah, we'll see. We'll see how it goes. Okay. 16.5. 16.5, we're really setting up some tools and rules that we're going to be using from here on out. Okay. And these come to us from, again, Fluid Dynamics, it's called the curl. Okay, so 16.5 is curl and divergence. Okay, the curl and divergence. Okay. So the curl is rotational motion through a vector field, okay, or a force field. Okay, and divergence is linear motion through a vector field. Okay, so curl is rotational motion and divergence is linear motion. Okay. Okay, so let's define these mathematically. Okay, so the curl if F, that's an F by the way, if F is equal to Pi plus Qj plus Rk, okay, is a vector field. On R3, okay, in space, and the partial derivatives of PQR okay, of PQ are all exist, then curl of F is the vector field on R3 defined by F equals, the curl of F, not F itself. The curl of F is equal to the partial of r with respect to y minus the partial of q with respect to z I minus the partial of r with respect to x minus the partial of p with respect to z plus j, sorry, there's a j there. Okay, plus the partial of q with respect to x minus the partial of p with respect to y, k. Okay, so this is the formula for the curl of f. Okay, now I wouldn't encourage anybody to memorize this formula. Okay, it's a very long formula. Okay, and this formula here is really a determinant. Okay, it's really a three by three determinant of a matrix. Okay, and so let's zoom in a little bit here. Okay, is a 3 by 3 matrix. Okay, so we're going to let del be the gradient matrix, or sorry, the gradient vector. Okay, so let del be the operator, the gradient operator, ddx of I plus ddy of z, or sorry, ddy of j plus ddz of k. Okay, and that's the gradient operator. Okay. Okay, so del crossed with f. Okay, so del crossed with f, and what was f? F was p plus q plus r. Okay, p I plus qj plus rk. Okay, if we cross product del with f, okay, we should get the curl formula that we have up here. Okay, and you should notice that you have something I minus something j plus something k, and you've got these subdeterminants, or these we call these cofactors. Okay, these cofactors of this 3 by 3 determinant. Okay, so it should be familiar that this is actually a determinant of a 3 by 3 matrix. So how are we going to set this up? Okay, well, we're going to go ijk. Okay, and then we're going to say, well, what's del? Del is going to be our operators, ddx, okay, ddy, and ddz. And then f is our matrix, or sorry, I keep saying wrong thing. F is our vector field. Okay, and so that's going to be pi, qj, and rk. And so if we take the determinant of this thing, okay, let's look at the I row and column. Let's get rid of the I row and column here. Okay, eliminate I, and then we're going to take the determinant of the cofactor. Okay, this is going to be, okay, ddy of r, right, minus, okay, ddz of q, and that's I, right? Okay, and we can see that, oh yeah, that's the first term in our curl. Okay, do a minus for j, right? It goes plus minus plus. minus for j, get rid of row and column here, and we get dd x of r minus ddp of z. Sorry, ddz of p. I said that backwards. Okay, minus, and that's j. Okay, and then we're going to do one last one here. Get rid of the k row and column, and we get dd x of q, okay, minus dd z, sorry, ddy of p. And that's k, and that's our curl. This is equal to the curl of f. Okay, so what do we know? We know that, okay, that the gradient crossed with f, the gradient operator crossed with f is equal to the curl of f. Okay, and that's how we work with this thing. So let's get a curl here. Okay, example number 1. F of x, y, z. Let me get some water. Okay, f of x, y, z is going to be equal to, this is our vector field. Okay, xzi plus xyzj minus y squared k. Okay, so I want to find the curl of f. Okay, so what's the curl going to be? Well, it's the gradient dotted with, or crossed with f. Okay, so we've got I, j, k. We've got ddx, ddy, ddz. Okay, and then we've got I, x, z is our ith component, x, y, z is our jth component, and minus y squared is our kth component. Okay. Okay, so now let's go through and cross product this thing. Okay, so what are we going to get? We're going to get cross off row and column for the i's, and we get dy of negative y squared minus ddz of xyz, okay, minus, oh, that's an I there, sorry, an I, okay, minus, okay, cross off row and column for the jth term, and we get ddx of negative y squared, x of negative y squared, minus ddz of xz, okay, and that's j, and then I'm going to continue below. I'm kind of running out of room here. Okay, below is going to be plus, okay, and then cross off the kth row and column, and we're going to get ddx of xyz minus ddy of xz. Okay, so now let's just take our partial derivatives. So our partial derivative on y of negative y squared is just negative 2y. So this is minus 2y. Okay, partial derivative of xyz with respect to z is xy. So this is minus xy. I. Okay, minus the partial derivative with respect to x of negative y squared, that goes to 0. Okay. because there are no, this is just the negative y squared is just treated like a constant, and the constant is derivative of constant is 0. Okay, minus the partial on z of xz, that's just going to be minus z. I'm sorry, minus x. Okay, so this is the negative of negative x, j. Okay, and then plus ddx of xyz, that's just going to be yz, minus ddy of xz, that's 0. Okay, so let's clean this up. This is negative 2y minus xy I plus xj plus yzk. Okay, and I could factor out a negative y in the first term if I really wanted to. I don't need to, but that is my curl. Okay, that is the curl there. Okay, so why is the curl important to us? Well, a couple reasons. Okay, the curl shows me, okay, so say that I have a silo of water. Okay, say that there's water in here. Okay, the curl shows me if this thing is rotating or not, and all of these particles, the curl creates a rotational force field for all of the particles in say this vat of water. You know, how fast are each of these particles rotating? You know, and are they doing it clockwise, or are they doing it counterclockwise, or is there just no rotation whatsoever? Okay, so again, fluid dynamics there. Now, the other thing that we want to know is, you know, is this thing conservative or not? Are all of the energies being conserved? And before we had this, we had a test for something being conservative, right? And that test was if for two variables, right, for two dimensions in the plane, okay, we had, say we had f is equal to pi plus qj, right? We had pi plus qj, and we said that if the partial of p with respect to y is equal to the partial of q with respect to x, we said that if this is true, if this checks, then we said that f was conservative. Right, then f is conservative. Now, what did it mean that f was conservative? It meant that there was a parent function or a potential function that we were able to find that where if I took the gradient of f, that was equal to our vector field. Okay, our vector field in 2 dimensions. Okay, so this was kind of our test, right? This was our test, was, you know, dp dy is equal to dq dx, right? I could rewrite this as dp dy minus dq dx, okay, is equal to 0. Okay, is equal to 0 there, right? dp dy minus dq dx, okay, was equal to 0. And if this thing equals 0, then we would say, well, yeah, it is conservative. Okay, well, similarly, what we can do is we can say that if the curl of f is equal to 0, then it is conservative. Okay, if the curl of f is equal to 0, in 3 space now, right? So we were able to get a test for 2 space to see if something was conservative in 2 space. Now we're stepping it up a notch into the 3rd dimension. And we're saying, oh, well, if the curl of f is equal to 0 in 3 space, then f is conservative. And what did it mean to be conservative? It meant that we could find del f, or that this was just, these were nice functions, right? They had nice partial derivatives. Okay, they had nice second order derivatives. Okay, and so they were just nice functions. Okay, that we could find a potential function for, that we could find a parent function for. Okay. Okay. So number 2 here, show that the vector field show that the vector field f of x, y, z, in 3 space, y squared z cubed I plus 2xyz cubed j plus 3xy squared z squared k is a conservative vector field. Keep spelling field wrong. Okay, it's conservative. Okay, so what do we want to prove? We just want to prove that the curl of f is equal to 0. So let's show that the curl of f is equal to 0. Okay. First we're going to show that this thing is conservative. Then find f such that del of f is equal to f. Okay, so then we're going to actually find, okay, we're going to say, can it be found? Well, yeah, if this thing is equal to 0, then the curl of f is equal to 0, then it can be found. And then if it can be found, well, what exactly is it? What is the potential function here? Okay, because if we can do the potential function, then we can use fundamental theorem, you know, and everything's nice. Okay, so then find f such that del f is equal to f. Okay, so let's go for the curl. Okay, the curl of f is equal to I j k d dx d dy d dz of y squared z cubed plus 2xyz cubed plus 3xy squared z squared. Okay, now I'm not going to write out the partials. I'm just going to take the partials, if that makes sense. Okay, so like for the first one here, if I cross this off and cross this off, right, then what are the partials here? What are the partials going to be? Well, I'm going to take this thing, okay, with respect to y, minus this thing with respect to z, right? So what is the partial with respect to y here, okay, of 3xy squared z, right? Well, isn't that 6xyz squared, right? And then minus, well, what's the partial on z, okay, with respect to z of 2xyz cubed? Well, isn't that the same thing? 6xyz squared, right? Okay, which gives me 0. So that's 0i. Okay, minus. Okay, now I'm going to do the same thing here. Here's the magic. I can get rid of this stuff. Look at that. Very good. Okay, cool. Magic of technology. Okay, what about J? Let's do J now. Okay, we're going to do ddx of k. ddx of k, that's going to be 3y squared z squared. Okay, and then we're going to go ddz of I. Well, that's the same thing, 3y squared z squared. That goes to 0. Okay, that's minus 0j. Okay, what about k? That's ddx, okay, ddx of this guy here, and then ddy of that guy there. Okay, so what's ddx? Well, that's just 2y z cubed. Okay, 2y z cubed, and then minus the exact same thing. When I do take the partial with respect to y, that's 2y z cubed, k, that thing becomes 0k, and so the whole thing is 0. And so what do we know? We know that f is conservative. Okay, we know f is conservative. Therefore, del f exists. Let's find del f. Well, let's find f. Okay, let's find the potential function here. Okay, so, well, what was little f? What was capital F? Capital F was our y squared z cubed I plus 2xy z cubed j plus 3xy squared z squared k, right? Okay, so what is this thing? This is f sub x. Okay, that's the first term there is f sub x. What's the next term? Well, that's f sub y. And what's the last term? It's f sub z. Okay. Okay, so we're saying that these things are that. So let's integrate these with respect to x, y, and z. Okay, so this is going to become xy squared z cubed. Okay, this thing, okay, so f sub x is equal to x squared plus, okay, some function of, we'll call this g, some function g of y z, right? Because we took the partial with respect to, shouldn't be the partial, it just should be f. Okay, we took the partial with respect to x, so we could have had some function of yz that just goes away. Okay, by undoing the x there. Okay, what about if we did, and then some constant k. Okay, what if we undid y here, f sub y? We integrated that. Well, that's just going to be xy squared z cubed. Okay, same thing. And then it's going to be some, we'll call this h of xz plus k. Okay, and then f is equal to, let's look at the last one here. This is going to be, okay, we want to integrate this with respect to z. So that's xy squared z cubed. The 3 goes away because we're going to go 1/3. Okay. And then plus, we'll call this, I don't know, m of y of xy plus k. Now we want to reconcile all these. Well, there are no extra terms here. Okay, so all of this goes away, and they all end up being this first term and then some sort of constant. So f is equal to xy squared z cubed plus k. And we see that that is conservative. If we took the partial derivatives of this thing, we would come out with our force field. Okay, and so it does check. Okay. Okay, we good? Makes sense? Okay. Insert more pages here. I've gone through a lot of pages already. Okay. Okay, let's talk about divergence. Okay, so what is divergence? Okay, divergence, if we look at, okay, say water flowing, okay, so positive divergence is water flowing out of an area. Oops. Okay, so this is positive divergence. Okay, negative divergence is water flowing into an area. Okay, and zero divergence is when water is just there already, and we say that there is no flow. Okay, there's no flow. Okay, in or out. Or what we could really say is that water is everywhere, and it can be moving. It's just moving through. Okay, it's moving through the area. Okay, it's just not stopping. And what we call this is we call this incompressible. Okay, let me make that a little bit bigger. This is when it's 0. We say this is incompressible. Okay, because you can't really compress water. Okay, I mean, you can put it under some sort of pressure, but you know, not a whole lot. So it's just saying, look, if it's 0, it's incompressible. There's no room for extra water to go into this silo or this vat. Okay, water's not flowing in or out; it's kind of moving through. Okay, or it's just not moving at all. So that's what divergence means in the real world. Okay, let's talk about it in the math world. Okay, if F is equal to Pi plus Qj plus Rk, so we've got a force field in 3 space, okay, is a vector field, okay, on R3, and dp dx, dq dy, that's a q, by the way, and dr dz exist, then the divergence of f is the function defined by the divergence of f is equal to dp dx plus dq dy plus dr dz. Now notice this is not a vector. Okay, this is a scalar. Scalar, not scalar. Okay, this is a vector, not a scale. I'm sorry, this is a scalar, not a vector. Okay, whereas the curl was a vector, okay, because it was cross product, it basically created another force field, a sub-force field, okay, a force field that described rotational energy in the system. Okay, this is a scalar that just describes, okay, a unit of movement. Okay, how much is this thing moving in or out of a system? Okay. Okay, are we adding water to the system? Are we subtracting water from the system? Or is the water from the system staying constant? Okay, in which case we say that the divergence is 0. Okay. Okay, so we can also rewrite this, okay, using del notation. Okay, the divergence of f is equal to del dotted with f. So this is, instead of the cross product del with f, this is the dot product of del with f, right? So whereas where del was what? What was del? Del was d dx. Okay, I plus, okay, d dy j, right? So this is del, okay, plus d dz k. And what is f? F is, do we count up here? Yeah, f is p, q, and r, right? So f is pi plus qj plus rk. So let's dot this. What happens when I take the dot product of this? Well, I just get d dx of p plus d dy of q plus d dz of r. Okay, which is exactly what we have up there. Okay, so the divergence. So let's dot product this. Okay, del dotted with f is equal to this. And so this is equal to, okay, dp dx, dq dy, dr dz, which again is the divergence. So it checks. Okay. So the divergence is del dotted with f. Okay, whereas the curl was del crossed with x with f. Excuse me. Okay, so let's find one of these. Okay, let's find the divergence. Okay, if my force field is x, y, z. Okay, if my force field is x, y, z equals xzi plus x, y, z, j minus y squared k. Okay, so there's my force field. We want to find the divergence of f. Okay, so what are we going to do? Well, we're going to take the partial with respect to x, okay, of this guy. So divergence of f is equal to del dotted with f, okay, which is going to be equal to d dx of xz plus d dy of xyz plus d dz of negative y squared. Okay. Notice there's no ij's and k's because again we're doing the dot product. Okay. So this is going to become z plus this is going to become xz. Okay, and then plus 0. Okay, I could factor out a z if I wanted to, and I get 1 plus x. Okay, and that's the divergence. Okay. Okay, let's look at a theorem here. Okay, if f equals pi plus qj plus rk is a vector field on R3 and P, Q, and R have continuous second order partial derivatives then the divergence of the curl of f is equal to 0. Then the divergence of the curl, taking the curl first and then doing the divergence on the curl. Okay, if this is a nice function, has nice continuous second order partial derivatives, and we take the divergence of the curl, it equals 0. Okay, let's do a proof of this. Okay. Okay, proof. Okay, so what was the curl of f? We defined it as, well, it was that 3 by 3 matrix, right? And when we did a 3 by 3 matrix, we got let's put it up here real quick. I, J, K, and then this is d dx, d dy, d dz, okay, P, Q, and R. Excuse me. Okay, P, Q, and R. So let's write this out. What's the curl here? The curl is going to be d r of with respect to x, k minus, oops, what am I doing? Sorry, this is wrong. This is with respect to y. D r dy, k minus d q dz I minus k dr dx minus dp dz. Okay, and then j. Okay, and then plus k dq dx minus dp dy. Right? Okay. Okay, right? Okay. And we want to take this thing now, and we want to take the divergence of that, right? Take the divergence of this. So what's the divergence of this thing? Well, the divergence of the curl is going to be the same thing, but now we're going to take our partials with respect to each of these, right? Okay, so let's take our partials with respect to each of these. D dx. Okay, so we're gonna dot product at the same time. So this is basically how do I want to write this? So this was the curl, and then the divergence of the curl is going to be equal to del dotted with the curl of f. Okay, so we're going to take del and dot it with the curl of f. So it really becomes this d dx of dr dy minus dq dz. Okay, okay, minus d dy of ddr with respect to dr dx minus dp dz, okay, plus, and this is with respect to z, of dq dx minus dp dy. Okay. So we're taking a partial on a partial. Okay. So partials with partials. Okay, so we're going to take a partial with respect to r, with respect to y, and then the partial of that with respect to x. So here's the notation for this. Let's kind of think of it like distributing. Okay, partials of partials. Okay, so we're going to take the partial of r first with respect to y, and then with respect to x. So we're going to go partial r squared, sorry, other way around. Partial squared r, okay, of partial of y and then partial of x, minus partial squared of q, partial of z, and then partial of x, okay, and then minus, okay, partial of partial of r, and then we take the partial with respect to x, and then the partial with respect to y, okay, and then plus, and there's a squared here, okay, partial squared p, okay, and then partial with respect to z, partial with respect to y, plus partial with respect to x, and then partial with respect to z. Okay, and then minus partial with respect to p. Okay, partial of p, first with respect to y, and then with respect to z. Okay, so now if this is continuous second order partials, then what do we know? Then we know that any of these r, q's, or p's, when I take a second partial here, so let's just look at this. If we take the second partial of f with respect to, say, x and then y, if they are continuous second partial derivatives, it doesn't matter which order in which I take the partials, they will be equal. Okay, that's why we needed that condition. We need this condition that, you know, they're continuous second order partials. If they're continuous second order partials, then we're good. Okay, then these two are equal. And what does that allow me to do? Well, it allows me to say that I took this thing first with respect to y, r with respect to y, and then with respect to x. But over here, I took it with respect to x first, and then with respect to y second. But those are the same. Same thing with the q's. I can cancel out the q's, and the same thing with the p's. I can cancel out the p's, and so the whole thing equals 0. Okay, so that is our proof. Okay, let's look at a vector form of Green's theorem. Okay, so vector form. Okay, so the vector form of Green's theorem. Okay, so what does Green's theorem say again? It said that if we have the positive oriented, okay, line integral of a vector field, okay, positive oriented line integral of vector field was equal to, and it was a closed, right, closed line, okay, and it created a boundary, okay, around, okay, around an area, okay, create a boundary around an area in the plane, then this was equal to the area of the boundary of the function dq dx minus dp dy, right, dA. Okay, that's what Green's theorem is. Okay, so it's basically, look, I have this line integral, okay, but we could turn that line integral into an area if we take our partials in such a way. Okay. Okay, so we want to get this, but we want to do it with vectors. Okay, with vectors. Okay, so okay, so we're going to say that this guy, f dot dr, okay, is going to be equal to p dx plus q dy, where F is our force field, equal to pi plus qj. Okay, so p is with respect to x, and q is with respect to y. Okay, p has all of our x terms, and y has all of our y terms. Okay. Okay, so what would be the curl of f here? Okay, for this function. Well, we're going to do ijk, and then we're going to do ddx, ddy, ddz. Okay, and then we have p, q, but we do not have k, but that's okay. We're just going to let k be 0. Okay. Okay, so now let's take our curl. Okay, so for y, this is going to be, okay, sorry, for I, this is going to be d dy of 0. Okay, so d dy of 0 minus dq, I'll just go d dz of q. Okay. Okay, I minus, what do we got here? We've got d dx of 0 this time. Minus d dz of p. Okay, and that's j plus, okay, let's go to the k term. This is d dx of q minus d dy of p. Okay, okay. So now what do we have here? Well, this thing goes to 0. I know that goes to 0, and this thing goes to 0. Okay, but this right here, this also goes to 0. Why? Why does that go to 0? What's the partial on z of q? Well, q doesn't have any z values. We're in two space here, right? So there are no z values, right? So if I took q is just a function with respect to x and y. And p is just a function with respect to x and y, right? Why is that? Because it's in the plane. Okay, because this is a function in the plane. So if it's a function in the plane, then since q was with respect to xy, q is qxy, right? Then when I take that partial with respect to z, that goes to 0. There are no z's. So that's treated as a constant. The same thing over here, the same reason over here, this thing goes to 0. Okay, p is with respect to x and y. Okay, and so that goes to 0. So the only thing that survives is this term here. It's the only thing that survives there. And so we have the curl of f is equal to dq dx minus dp dy, okay, k. Okay. So we're close to what we want. We just have this extra k term here, right? So we have this extra k value. Okay, so this is a vector in the k. I'd like this to be a scalar and get rid of that k. So the way that I do this is I'm going to take this curl and I'm going to dot it with the identity vector 0, 0, k. Okay, dotted with 0, 0, k, which is really just k. Okay, I'm going to dot this with 0, 0, k. And then what does this allow me to do? Okay, or dotted with, I should say, 0, 0, 1. Okay, so, okay, which is the same thing as taking the curl of f. The curl of f and dotting that with k, right? So dot it with k. Well, what is k? K is just the vector 0, 0, 1. Okay, if I dot it with that, that gets rid of the k. Okay, because the only term that I have in the curl of f is this kth term, and then I'm dotting it with 1. So I'm basically multiplying by 1, and it turns it from a vector into a scalar. Okay, so here's the idea, is that we could rewrite Green's theorem, f dot dr, as the double integral over d of the curl of f dot k dA. Okay, so that's an alternate form of Green's theorem. We could say C. Okay. Another form, okay, of Green's theorem is this one here. This takes, instead of just a field, the vector field, we're gonna dot that vector field with the normal vector. Okay, so again, let's use a picture here. Okay, we're gonna get this guy here, and we have a tangential vector at that point, t of t, and we have a normal vector at this point, okay, n of t. Okay, or little n. We'll do little n there. Okay, tangential vector and a normal vector. Okay, so as we go around this thing. Okay, we have our tangential vectors and our normal vectors. Okay, the line integral of the normal component, okay, line integral of the normal component of f along C can be expressed as, okay, a positively oriented line integral, okay, around a closed field, where we take our field and we dot it with n with respect to S, with respect to this surface, okay, is equal to, okay, the double integral of d of the divergence of f dot dA. So this is another way, another form of Green's theorem in a way. Okay. Okay, and I'm not going to go into the proof of that. That's kind of beyond the scope of this course. Okay, just know that it exists. Okay, that's 16.5. Okay, let's move into 16.6. Okay, so I'm only going to do half of 16.6 today. Okay, because I don't want to get so far ahead. Okay, so I'm going to jump into half of 16.6. Okay, and then we'll pick up next time. Okay, where we left off. Okay, so I want to talk about parametric surfaces, okay, and their areas. Okay, so parametric surfaces. Okay, parametric surfaces. Okay, I want to parametrize, okay, the sphere. So find a parametric representation okay, of the sphere x squared plus y squared plus z squared equals r squared. Well, let's do a squared. Okay, for the radius, because okay, that'll be the radius of the sphere. Okay, so how can we parametrize this? Okay, we want x to be equal to something, y to be equal to something, and z to be equal to something, right? Okay, so we're just going to use our spherical coordinates to do this. This is going to become a times the sine phi times the cosine of theta. Okay, this is going to be a sine phi sine theta. This is going to be a cosine phi. Okay, where phi goes from 0 to pi. And theta goes from 0 to 2 pi. Okay. Okay. The corresponding vector equation, okay, vector equation, okay, is r of, now you can see why I didn't want to use r for my radius, okay, because this is going to be our vector equation, r, okay, r of phi theta, okay, equals, a is a constant, by the way, it's not a variable, okay. Okay, r theta is equal to a sine phi cosine theta I plus a sine phi sine theta j plus a cosine phi k. Okay, where the domain D is the rectangle, okay, D equals 0 pi by 0 2 pi. Okay, where phi are the circles of latitude, okay, and theta are the circles of longitude. Okay, so that's our vector representation of the sphere. Okay, so very similar to spherical coordinates, but now we're just saying, look, on the sphere, okay, how can we get each of these? How can we get each of these points using a vector? Okay, what's the vector representation of this? Okay, and that is this. This is our vector representation in 3 space. Okay, it's going to build our sphere. Okay, number 2. Okay, find a vector function that represents the elliptic paraboloid z equals x squared plus 2y squared. Okay, let's find a vector function that represents this. So first I need to parametrize this. Okay, so to parametrize this, I'm just going to do this. I'm going to say x is equal to x, y is equal to y. Okay, and I'm just going to parametrize this in 3 space. And z, well, what is z equal to? Z is equal to x squared plus 2y squared. Okay, so putting this as r of xy, okay, two variables, okay, r of xy, okay, r of xy is equal to, okay, xi plus, okay, yj, okay, plus x squared plus 2y squared. Okay. Okay, and that's it. That's a vector representation. Okay. Now sometimes there's more than one vector representation. Okay, we could have used we could have used r's and thetas here as well. We could have used polar coordinates. Okay, but this works just as well. Okay, let's do number 3 here. Okay, find two different parametric representations okay, for z equals, okay, 2 times the square root of x squared plus y squared. Okay, we want to find two different parametric representations. Okay, so the first one is going to be the easy one. Okay, r of xy is equal to xi plus yj plus 2 square root of x squared plus y squared k. Okay, that's the first one. Okay, the second one here, okay, we're gonna turn this into polar coordinates. Okay, so so x equals r cosine theta, y equals r sine theta, okay, and z is equal to what? Well, z is equal to 2r, right? So z is equal to 2r. I could plug that r cosine theta in and that r sine theta in, and we get z equals 2r. Okay, so r of r theta, okay, is equal to r cosine theta I plus r sine theta j plus 2rk. Okay, and that's the second parametric representation. Okay, next one. Surfaces of revolution. Okay, consider the surface S obtained by the curve y equals f of x about the x-axis. Okay. If of x, y, z, no f, sorry. If x, y, z is a point on S, then x equals x, y equals f of x cosine theta, and z is equal to f of x sine theta. So we have this curve here, right? And we're revolving it. Okay, about the x-axis. Okay, we're saying that you know, x is equal to x. Okay. Y is equal to f of x cosine theta. Okay, and z is f of x sine theta. Okay. This is z and this is x. And this is y. It's kind of oriented differently, simply because I put the x and the y, you know, on the plane, and z is coming out at us. Not our general orientation, but that's okay. It works. Okay, but just know that, you know, this rotation is in the xz plane. Okay, so I'm sorry, in the YZ plane. The rotation has been the YZ plane. We're going out X. The rotation, okay, is in the XZ plane. I keep saying that. It's in the YZ plane. Okay, so rotation. In the YZ plane. Okay, so that's why this f of x is getting rotated in the YZ plane, and we can find its components using cosine theta and sine theta. Okay. Okay, so number 4 here. Find parametric equations for the surface generated by rotating y equals sine x about the x-axis. Okay, so what's our parametric equations? Well, our parametric equations, x equals x, y equals, okay, f of x sine, or f of x cosine theta. So this is going to be sine x cosine theta. And what's z is equal to sine x sine theta. Okay, where x is going, okay, from where to where? Well, I'm going to just do one rotation of x, one period here, okay, of my sine function. So I'm going to let sine, I'm going to let x go from 0 to 2 pi. That gives me one rotation, or one cycle, I should say, of the sine function. And then what's theta going to go from? It's the same thing. Theta is going to be rotating around a circle, and so 0 to 2 pi. Okay. Okay, let's look at parametric forms of planes. Okay, how would we do a parametric form of a plane? Okay. So let's talk about tangent planes. Okay, tangent planes to a surface. Okay, the tangent plane to a surface is the plane that contains the tangent vectors r sub u equal to the partial of x with respect to u naught v naught k I plus the partial of y with respect to u k u naught v naught j plus the partial of z with respect to u naught v naught k. Okay, and our v is the same thing, but just with the v's. U naught v naught I plus dy dv u naught v naught j plus dz dv u naught v naught k. Okay, so this is how we're going to write our plane. Okay, our tangent plane in terms of these vectors. Okay, tangent vectors. Okay, where RU cross RV is a normal vector to the tangent plane. Okay. Okay, and obviously the point that we're going through, okay, the point of contact is this mu naught v naught. Okay, so the plane and the surface both contain the tangent vectors, but I'll put also here. Also, the point of tangency is this mu naught v naught. Okay, that's the kind of the point of tangency there. Mu naught v naught. Okay. Okay, number 5. Find find the tangent plane to the surface okay, surface x equals mu squared, y equals v squared, and z equals mu plus 2v. Okay, so we've parametrized u, x, y, and z into u and v. Okay, we've taken it from 3 variables into 2 variables. Okay, at the point, okay, 1, 1, 3. Okay, so if x equals 1, u squared equals 1, then u would equal plus or minus 1. If y equals 1, v squared equals 1, then v equals plus or minus 1. If z is equal to 3, then u plus 2v has to equal 3. Well, what's the only way that we could have u plus 2v equaling 3? And that's if u and v were equal to 1. So that's our winner there. We don't deal with the negatives because that doesn't satisfy our third condition here. Okay, u is equal to 1 and v is equal to 1. Okay, so that's our values, okay, for our parameters. Okay, so r sub u, okay, r sub u again is equal to, okay, dx du okay, of, okay, uv okay, of, what do I want here? Okay, of u naught v naught I, okay, right? Okay. And then plus dy du of u naught v naught j plus dc du of u naught v naught k. Okay. Okay, so we're going to take, okay, dx du of our x component, okay, dy du of our y component, and then dz du of our kth component, okay, x, y, z. Okay, so r sub u is going to be the partial derivative of x with respect to u. What's the partial derivative of x with respect to u? Well, that's 2u, okay, 2ui, plus, okay, of that function there, okay, with respect to u and v. Okay, dy du, what's that one going to be? Well, that's 0, because there is no u. Okay, 0, okay, j, okay, plus the last one here with respect to u, that's just 1k. Okay, so that's just k. Okay, so that's r sub u. Okay, r sub v, it's the same thing, but with respect to v's. Okay, so r sub v, this one's going to be 0, I. This one's going to be 2v, j, and this one's going to be 2k. Okay. And now in order to find the normal vector to this plane, okay, in order to find the normal vector to this plane, okay, I want to cross these. Okay, I want to cross these and then evaluate them for u and v. Okay, evaluated for u and v. So let's do the cross product of these. Okay. So we could evaluate them right now if we really wanted to. Okay. Well, let's do that. Let's evaluate them. Okay, 2u, what did we find u to be? U was 1, right? So we evaluate that at 1. So that's 2 times 1 is 2, so that's just 2i plus 1k. Okay, the j's go away. This over here is going to be, RV is going to be 2 times 1, okay, which is just 2j plus 2k. Now let's cross this. RU cross RV. Okay, I, J, K. Okay, what's RU? RU is 2i plus k, so that's 2, 0, 1. This is going to be 0, 2, and 0, 2, and what else we got here? 0, 2, and 2. Yeah, 0, 2, 2. Okay, so now let's do the cross product on this. Okay, this is going to be 2i. Cross product, what is it going to be? Minus, cross off row and column here, that's 4j. And then do the k's here, that's 4k. Okay, so this is going to be my normal vector. Okay, my normal vector is this guy. I could write it in component form, 2, negative 4, 4. Component form. Now, how did we find a normal, how did we find the equation of a plane given the normal vector and the point before, right? Well, it was, okay, it was normal vector ABC, right? A times and x naught, y naught, z naught, right? And it was A with x minus x naught, B times y minus y naught, C times z minus z naught was equal to 0. That was the equation of our plane in 3 space. Okay, where A, B, and C is the normal vector, okay, to that plane. So here we just plug in the numbers. So this is 2 times x minus 1, minus 4 times y minus 1, plus 3 times z minus 3. No, not 3. It's 4. 4 times z minus 3 is equal to 0. Okay, I could clean this up if I wanted to. I don't have to. I could be done at this step. But I'm going to clean this up a little bit algebraically. Minus 2 minus 4y plus 4. This is plus 4z, excuse me, plus 4z minus 12 is equal to 0. Okay. So we've got, what have we got here? So this is, did I mess up somewhere? I did, didn't I? This, I'm sorry, the first one here is a minus 2. This should be a minus 2. Because when you do your rows and columns, it's a 0 minus 2. Okay, so this should be minus 2. Minus 2 plus 2. Okay, so just want to make sure I get the correct answer. That's a minus 2, minus 4, plus 4. Okay, so minus 2x, okay, minus 4y, plus 4z. Okay, and then this is 2, 4, and this is minus 6 equals 0. Okay, I could divide everything through by 2 and then toss the 6 to the other side and divide that by 2. Or let's divide everything through by negative 2, actually. Negative 2, negative 2, negative 2, negative 2. Okay, and then we're going to get x plus 2y minus 2z is equal to negative 3. Okay, and that's the answer. Okay, and that's the normal, that's the tangent to, that's the tangent plane to my surface, okay, at the point 113. Okay, so here's a parametrized surface. Okay, parametrized surface in terms of u and v. Okay, and then using 2 parameters. Now this only works with 2 parameters. You can only have it in 2 parameters. That's kind of why we went through the whole thing before for all these other problems, where we isolated it in 2 parameters so that we could find the tangent plane. Okay, so in order to get the tangent plane using this method, we have to have our equation with respect to 2 parameters only. Okay, they could be x and y. Okay, they could be uv. Okay, whatever it is you want, but you know, theta and r, whatever those 2 parameters are. Okay, we want to isolate to 2 parameters, and then we can find the tangent plane, just like finding tangent lines. Okay, for in 2 space, we're finding now tangent planes in 3 space using this method. Okay, using our partial derivatives. Okay, and our cross product. Okay. Okay, that's it for me. I'm only going to go halfway on 6. We're going to talk about surface area when we come back on Tuesday, and then we'll be close to finishing up the material. So another week and a half, and we should be good. Okay. Okay, I'll see you guys later.